from me too. My name is Garini, and I will continue from Dimitris Pitilakis in the geotechnical, let's say, point of view, but I will also include some near-fault phenomena that we observe, and also some geotechnical observations from the Pazarcik magnitude 7.8 earthquake. So just glance over what I will present you. We will discuss some near-fault phenomena, and then their effects on the recorded ground motions. And we will end with the tilting of buildings in Golbesi and the mechanisms why this happened, and the soil liquefaction in Golbesi. So this is just an overview map. You can see with the stars the first Pazarcik earthquake of 7.8, and with the black line is the fault that induced this huge earthquake. And later, 9 hours later on, as our colleague Professor Eberic said, 9 hours later, another big earthquake on the north, the Elbistan earthquake of 7.5 magnitude happened. Also in a completely different fault. So let's start with some near fault phenomena. This is a detail of the faulting that induced the 7.8 earthquake, and let's make a dive into some seismotectonic phenomena. First, you should know that this earthquake, this big earthquake, started from this small surface, this small segment. This blue segment was ruptured, and not only that, but also a very, let's say, a strange phenomenon called super shear was observed and was proved also by this paper by Aris Rosakis from Caltech. And then what happened? The fault branching. The ruptured here in this joint starts a bilateral propagation shown with the red arrows and the yellow arrows. This is also a well-studied phenomenon from the seismologists. For example, in the Landers 1992 earthquake in California, there was also this branching effect where we have the rupture and it goes to a point and then it propagates to two different directions. This is also what happened in this case. And just to mention that this second segment with the yellow arrows dips down to the east and ends up to Antakya. And we will see later on that this is having a special effect. This is the map with the outstanding stroke motion network of Turkey. We in Greece are very envy of such a plethora of recording stations, 857 recording stations. The area of interest is shown here, and let's move closer. As you can see along the dust line, which represents the fault, we have a lot of triangles, which are the acceleropographic stations. So we have near fault or even on the fault recordings, at least in 25 stations. And this is a world record for such an earthquake. This is just a summary plot. On the vertical axis is the peak ground accelerations in percentage of G, and in the horizontal is the distance from the fault. And we are interested in these narrow region, which represents the near fault motions. These are the most devastating motions to our structures, geotechnical or structural ones. So let's move on to the ground motions and see what is the effect, the outcome of these near fault phenomena to the recorded motions. So let's see some strong motions that were recorded along the fault rupture. So we will start with the station shown inside the circle from the small first fault segment that was ruptured close to Pazarcik. On the top, I am showing the acceleration time history, and on the bottom, the velocity one. So please notice that we have a first wave package that it is induced by the rupturing of this small first segment, and then we have a second wave package, which is induced by the propagation of the rupture along this large fault, which is more than 300 kilometers length. And this rise to a velocity pulse of such a magnitude. And if we move on to a close station in Turkoglu, then this is what it is recorded. We can also observe a first wave package that was induced by the rupturing of this first segment, but now you can see it's smaller because it's far away from this station. And then we have a greater wave package because of the rupturing of this segment, the second segment. And we can also see a third one from the propagation of the seismic waves from the third rupturing segment of the north. And as a result, we have also great velocity pulses. And if we move down to Antakya, we are at the end now of the rupture, and let's see what it is recorded here. So this is from a station, and okay, let's go back just a second. Please look at this duration from 30 seconds up to 90 seconds. So we're talking about 60 seconds total duration, which is expected for such a large magnitude earthquakes. So if we go to Antakya, what's happened? That we have just one wave package, not two or three that we had before. Why? And second, we have great acceleration, big acceleration, and also we have big velocity with velocity steps up to 3 meters per second. This is world champion. Only some records I know from the 1999 Chichi earthquake in Taiwan present such big velocity steps. And maybe this is because of this particular station. So let's see another one from Antakya. The same thing. We have a small duration, not 60 seconds, but 15, 20 seconds, but higher, well-established acceleration pulses. And what is more, also big velocities in terms of absolute velocities and also of velocity steps. So the question is, why is this happening in Antakya? Why the recorded motions in Antakya are of relatively limited duration for such a huge magnitude? And the answer is because of two events, two phenomena. First, the forward rupture directivity effects that it was observed in almost all the recordings of Antakya, and second, because of the super shear effects in some, not in all the stations. And let's see graphically, in brief, what are these phenomena. So first, What is the forward directivity? Let's say that we have in this sketch a fault. This is the line, and we have the epicenter. We have the source of the rupture starting and moving bilateral in two directions, as we have in our particular case of the Pazarcik 7.8 earthquake. So if we have two sites that we have records, site A and site B, the source of the rupturing is propagating with a velocity that is very close to the shear wave velocity of the rock. This is the most usual case. And as the seismic waves propagate from the source, if we see the record in site A, we will observe quite medium to small acceleration, but large duration. And if we move on to a later site like B, just to keep in mind that site A is something like Turkoglu that I saw you before, and type B is something like Antakya. What happens? Well, the wavefronts that emanate from the moving source are generated at different time instances, but they arrive at site B at Antakya, for our case, almost at the same time. Why? Because it happens constructive interference of waves. And so there is a forward directivity front. This is a phenomenon very similar to the well-known Doppler-Fizeau phenomenon in physics, in the sound propagation. And as a result of this phenomenon, we have in the recording short duration, not 60, 70 seconds of duration, but 30 seconds of duration, but well-defined long period acceleration pulses with large amplitudes. And what happens with a super shear? What is it? Well, Aris Rouzakis, a professor from Caltech, at 1988 first noticed this phenomenon. And what he observed that in some cases, extreme cases, do happen the rupture, the source of the rupture to move with larger velocities than the shear wave of rock, not 0.9 than we have before, but up to 1.2 or 1.6 the shear velocity of the rock. And in this case, what's the result? That the rupture, as it moves faster than the shear waves, then catches the seismic propagating waves, and we have an overlapping effect of the wavefronts. As a result, it is shaped, it is developed a Mach front. It's something similar to a supersonic shock. And what's the result of these effects on the recording motions? Because this is what we're interested in. Well, the parallel component of the recording motion is greater than the normal, especially we see that in terms of the recording velocity, the peak ground velocity of the fault parallel component, it's greater than the peak ground velocity of the fault normal. And the ratio of these peak ground velocities is called the Mach number of the record. So, for example, for the motion that I saw you before, for Antakya, this is the acceleration and velocity time history on the left. This is almost the fault parallel component. So the fault normal component is shown on the left-hand side, and you can see we have almost the same acceleration time history, but look at the velocity time step. Look at the velocity time history, also in absolute values, it's 1.5 in terms of 0.8. So it's almost double the velocity time history. And if we move on to the elastic acceleration response spectrum, this is also depicted by the fault parallel component spectrum to be greater in all this yellow shaded region than the fault normal. And this is due to this super shear effect. So this is a map of Antakya. With the red are all the recording stations from the Afadan earthquake and the PGAs that were recorded. And with this double turquoise line is the fault projection. So we had the super shear effect in these three sections, in these three stations, not in all of them. And this is why we have these peak values and more detrimental in the fault parallel, not the fault normal. So numerous types of geotechnical damage. I will not stay here because Professor Pitilakis, Dimitris present this before. And we will go to Gölbaşı. Also, Dimitris present this, and Professor Eberik. I will show you in more detail the tilting mechanism of the buildings. So let's start. This is from the Google Earth, the lake and the city. And if we go to the center of it, this is a viral photo from the internet after the second or the third day after the February 6th earthquake. You can see the rotating building here. And if we move closer, we can observe first that there is no structural damage. And second, that this building is founded by a flat slab foundation, and there is not even a crack in the foundation. And this is representative of the motion of the building. It is moved like a rigid block. And this is how a sketch, how it moves. And if we go to the mechanism, a sketch of the mechanism of what happens, well, we have the building and the inertia acting on the center of the mass. And because of the asymmetric embedment here, we have the sidewalk on the front, and then we have on the back in a lower level the road. Then there is the rotation of the structure as a rigid block on one side, not on both sides, because it cannot rotate on both sides because of this asymmetry in the soil level. And what happens in the front, also Professor Eberik mentioned that very eloquent, that we have a soil heave, a bulge of the soil. And on the other hand, we have a bearing type of capacity failure of the soil. And what happens on the front? Why we have this soil bulge? Because of the compression forces that are acting on the soil mass in front due to the kinematic boundary constraints. We have this building kick back to the soil here, so it compresses, it acts some compression motion to the soil. Another photo, you saw this photo before from Pitilakis, and this is on the right-hand side, a sketch of what happens. We have a rigid block rocking oscillation type. Professor Macris also and Professor Gazetas have studied this type of systems, among others. Another case, this building, it's a side view. You can see it rotates and go and rests up to the neighboring building. And if we see it on the front view, you can see the big rotation. And let's close with the soil liquefaction and lateral spreading. If we go to the near Golbashi Lake, to these places, we have lateral spreading. This is from a road very close to the Golbashi Lake, and you can see here the cracks, and this is with the arrows, the direction that the soil moves. And what is the mechanism of lateral spreading because of soil liquefaction? This is a beautiful sketch. I steal it from Professor Gazetas. You can see on the top what happens. We have the excitation propagating upwards, and in this dotted red, it's a soil layer that it's quite soft, and of course we have on the top or very high the water table, and as a result the pore pressure becomes equal to the effective stress, and this layer is liquefied. And as it liquefies, what happens? The upper crust starts to oscillate horizontally. And as this progresses, as this phenomenon progresses, what happens? Well, kinematically, this soil crust moves towards the waterfront, and we have this kind of failure. Well, from above, what we could see something like that. This is from the Google Earth. This is the Golbashi Lake, and you can see here all the waterfront that moves toward the lake because we have liquefaction in a lower level, and sometimes this liquefaction we have remnants on the top of the soil ejector. Professor Pitilakis shows you some of these. And if we go to this region, we can see the soil liquefaction ejecta on the surface and the soil cracks. This is from the top. If we go to this is what we see. Submergence of this building. This was a two-story building, and you can see here just the first floor. Because of the lateral spreading, it moves towards the lake. So now it has a pool all around. Nice. And from another view, the lateral spreading, and you can see the trees, and here the soil movement and the direction of it. And here, a very rough estimation of the soil displacement could be made if we go and add up and sum up here the opening of the cracks of the soil cracks on the surface. So I end, and I will have to pay acknowledgements first in the Technical Chamber of Greens, along with NTUA and ETAM, for the financial support and organization of this trip. Of course, AFAD, our Turkish colleagues, for the immediate and open publishing of a huge number of accelerograms, which was of unprecedented quality. And of course, to Emeritus Professor Gazetas, he was an inspiration to this journey. And also to Professor Ioannis Anastasopoulos for sharing his observation and photos from the Golbashi, lateral spreading, and Sisi Nicolaou. So with this, I would like to thank you for your attention.